All right, back to our problem, in which we're supposed to apply the impulse momentum theorem, presumably. We've got a hockey puck on a horizontal in the xy plane frictionless ice rink, and a force which has an x component of 2 newtons, y component of -3 newtons is applied for 4 seconds. If we know the initial velocity components, can we find the final velocity x and y components using the impulse momentum theorem? And here I've got the one version of the impulse momentum theorem. And it says the net impulse is equal to the change in momentum. The net impulse in this case, well, that's just the impulse delivered by all of the forces that are being applied to the puck during its motion or during that time delta t. In this case, the delta t is the 4 seconds that are mentioned. So we've got a weight force, a normal force, and I didn't know what to call it, so I just call it the force, the one that's mentioned with the given components. We've got an impulse delivered by all 3 of those, but notice the impulse is proportional to the force that's being applied to it, and the weight force balances out the normal force. So the impulse due to those 2 together cancel because the forces cancel. So the net impulse in this case is just equal to the impulse delivered by the force. And that's equal to, can be computed by the average force being applied. And in this case, since the force is constant, the average is just equal to the components that were given times the time interval that elapses. So that's equal to mv final minus mv initial. So let's apply that up here. The average force x component is just 2 newtons, and the average force y component is -3 newtons. If we multiply those 2 times the 4 seconds, we get 8 newton seconds and -12 newton seconds for the x and y impulse components. And the impulse momentum theorem says that that's equal to m vx final minus vx initial and m vy final minus vy initial. And we can use that to solve for Vx final and Vy final because we know the initial velocity components and we know the mass of the puck. And when we do that, we get Vx final is minus 1.4 meters per second, Vy final is minus 3.4 meters per second. All right, I put this in here just to remind me of what to say. You may think you have pretty good intuition about momentum because you have good intuition about mass and velocity. So let's check that out. Momentum is sometimes a little bit trickier than the ideas of just mass and velocity, even though it's just the product of the two. So let's do some voting questions associated with momentum and possibly the impulse momentum theorem. Here we have 2 carts. One has twice the mass of the other one, and they're on frictionless tracks. If we push one cart for 3 seconds, and then we push the other for the same 3 seconds, and we exert an equal force on each, how does the speed of the light cart compare to the speed of the heavy cart? Is it larger, equal to, or smaller than? The answer is the light cart has a larger speed, and that's because, by definition, we push with the same force for the same amount of time on each of them, so we deliver the same impulse to each of the carts. And that means that the change in momentum of each of the carts is the same, but the one that has the smaller mass must have the bigger change in velocity, and therefore the speed of the light cart is going to be larger than the speed of the heavy cart. You could work that out on paper if it's not clear just doing it there. Solve for V final in terms of V initial. We could set V initial equal to 0 in this case, so imagine this term isn't here. This side is the same for both of them. Whichever one we divide by a larger mass will have the smaller V final. Similar question. If we have 2 carts, masses m and 2m on frictionless tracks again. We push one cart for 3 seconds, the other for the same length of time, so it's the same setup as before. How does the momentum of the light cart compare to the momentum of the heavy cart? And the answer is it's equal to it, because the impulse momentum theorem says that the net impulse delivered to it, and of course the weight force and the normal force from the track cancel out. So the net impulse on each cart is just the impulse due to the force that I'm applying. So the net impulse is the same on both. That means the change in the momentum is the same for both. They started out with 0 momentum, so they have the same final momentum in each case. That doesn't mean they're moving at the same speed, but they have the same final momentum. Third question. Suppose a ping pong ball and a bowling ball are rolling toward you. Both have the same momentum, and you exert the same force to stop each. So we have to push with a certain force, maybe 5 newtons, for as long as it takes to stop them. How do the time intervals to stop them compare? Does it take less time to stop the ping pong ball, equal time, or more time to stop the ping pong ball? In this case, it takes both the same amount of time, and that's because in this case, if they have equal initial momentums and their final momenta are both equal to 0, the change in momentum is the same. We're applying the same force to stop each, and therefore if we solve for delta t, we would get the same delta t for each one. So both take the same time here. Well, of course, looking at them, if you see a bowling ball rolling toward you and you see a ping pong ball with the same momentum rolling toward you, the ping pong ball is going at a huge velocity, whereas the bowling ball is just barely moving. So that's what it would look like if they had the same momentum. All right, here are 3 different situations. In the first situation, 1, we've got a ball moving at speed v, and we apply a force to it to bring it to rest. Situation 2, the same ball is projected from rest so that it moves at speed v. So in one case, it's moving at 3 meters per second and we slow it down to rest. The second case, we increase its speed from rest up to the 3 meters per second, say. And in the third case, the same ball is moving at 3 meters per second. We slow it down until it stops and then project it in the opposite direction at 3 meters per second. And the question is, in which case does the ball undergo the largest magnitude change in momentum? We've got several combinations of options there. The correct answer here is 3. The change in momentum is largest in case 3. And sometimes people get the wrong idea about this because it seems like the change in momentum might be 0 because it started at speed v, it ended at speed v. It really didn't change mv. But the point is here that momentum is a vector, and so if we imagine something moving along the x direction and it's moving with speed v in one direction and then it totally switches to speed v in the other direction, that's actually a big change in the momentum. Here's one way to think about the 3 different cases. Let's have plus x going to the right. Just for simplicity, we'll take the mass of the object as 1, and let's calculate the change in momentum for each one of them. So I'm going to imagine situation 1 up there. Initially, the ball is moving to the left, so its x initial component is velocity component is minus 1 meter per second, and then it's brought to rest, so its final velocity x component is 0. Situation 2, it starts at rest and then it ends up being projected to the right at 1 meter per second. And situation 3 would be like it's moving to the left, and then after slowing it to rest and then pushing it in the other direction, it's moving to the right at 1 meter per second. Those are similar to the descriptions at the top, or consistent with them. Let's calculate mv final minus mv initial and see which one has the biggest of this. In the first case, we get, when we do Vx final minus Vx initial is negative in this case, so we have a minus a negative number, we get plus 1. In the second case, we have Vx final is 1, Vx initial is 0, so we get the magnitude of the change in momentum is 1 again. Whereas in the third case, we have the final momentum is 1 and the initial momentum is minus 1, so we have 1 minus minus 1, that's the same as 1 plus 1, which is 2 meters per second in this particular case. So that's an explanation of why 3 is the case. Zero change in momentum means you have the same x component if you're moving along the x direction. If you switch x components, that's a huge change in momentum. So that's something to keep in mind, that people often get confused, because even though your speed isn't changing, you are changing your momentum via la left. All right, let's take a break.